In the beginning of this section, we explored the idea of the area under a curve being a function of x, and we defined it to be the definite integral from a to x of some integrand f of t with respect to t. Now, the fundamental theorem of calculus part 2 said that we could evaluate this definite integral by finding the antiderivative, capital F, evaluating it at the upper limit, in this case is x, and at the lower limit, in this case a. What happens though if we try, or we do, take the derivative of this function? Well, now that's the derivative with respect to x of the definite integral, or the derivative with respect to x of this thing that we just now evaluated. From the evaluation end, the derivative with respect to x of capital F of x is simply f prime of x, and the derivative with respect to x of f of a, which is just a number, is 0. So f prime of x, we saw in the fundamental theorem of calculus part 1, is lowercase f of x. It is simply the integrand. So on a basic level, what this part 1 business of the fundamental theorem of calculus says is that if we take the derivative of an integral, we are left with just the integrand. So let me show you an example here. We want to find the derivative of y with respect to x, where y is defined as the integral of some function. So we want the derivative of y with respect to x. That will be the derivative with respect to x of the definite integral from 1 to x of 1 over t dt. Now, as long as x is greater than 0, this function exists and is continuous. In fact, for this one special case, we know the antiderivative of 1 over t. So we can take the derivative with respect to x of the antiderivative. 1 over t is the natural log of t, and we'll evaluate this from 1 to x. So still holding the derivative operator out here, let's evaluate it. The natural log of x minus the natural log of 1. The natural log of 1 is 0. So now we're looking at the derivative with respect to x of the natural log of x. And this derivative, as you all know, is 1 over x. So we took a long road to get to the fact that when we do the derivative of the definite integral from a fixed value to x, we just replace the variable in the integrand for x, and now we have the derivative of the definite integral. So it makes it a lot easier to do part 8. In fact, the only way we can do example 8 to find the derivative with respect to x is to take the derivative with respect to x of the definite integral. Well, we don't know how to integrate this. It's continuous from 0 to x. There must be some function that has a derivative that is this, but I don't know what it is. So by the fundamental theorem calculus part 1, we say, well, the derivative of the integral, those are inverses of each other. They're inverse operations. It's like squaring and square rooting in the same step. Since it matches the theorem says that we have to start at a number here, a constant, and end at the variable here, which we do. We can just apply the theorem, which said that this will just be the integrand at x, which means we replace the variable for x. So this is the square root of 1 plus x squared. The derivative of the definite integral gives us the integrand. Here we want to take the derivative of y with respect to x. So that's the derivative with respect to x of the definite integral from the square root of x to 0 of the sine of t squared with respect to t. We're pretty close to being able to apply the fundamental theorem of calculus part 1, which says that these guys are inverses of each other. But we don't meet the condition that we start at a constant and end at a variable. This is not the situation here. They're in the wrong place, so we need to switch these limits. we can do that. Hold the derivative operator out here and switch the limits from 0 to the square root of x, sine of t squared dt. But to do that, it will cost us a negative sign. That's one of the properties of definite integrals. Now, though, it matches. So this is negative, the derivative with respect to x of the definite integral from 0 to the square root of x of the sine of t squared with respect to t. Matches the theorem. Which is the fundamental theorem of calculus. Part 1 matches because it goes from a constant to a variable. Means we can sub the variable right in there for our integrand variable. So we still have a negative, but the derivative and the definite integral are gone. The sine of the square root of x all squared, which is negative sine of x, to find the derivative of that definite integral. This is a weird concept for students. They say like, hey, why can I just make this simple substitution, and why does this one cost me a negative and the other one did not? So it matters which guy's in which spot. And the reason that we like this is because if we cannot find an antiderivative, or we can't express this thing in closed form, antiderivative, we can still take the derivative of it. Like we might have functions wandering around that are just in integral form, and we don't know what to do with those, but that's a perfectly fine way to define a function. Like this thing has a function, it exists, we just don't know what it is. By defining it this way, we can still recognize that we can take the derivative of it, we can do other things with it, and it makes it a little handier. So for those of you that are taking differential equations, partial differential equations in the future, you might run into this idea a couple more times. For us, we just have nice little examples in the end of the section just to practice. Number 7 is a good example because you can find the antiderivative and then differentiate it and find out that you get just the integrand anyway.